Hey y'all, welcome back. On tonight's homework, we are solving systems of linear equations primarily through the substitution technique. Our first few problems here are not asking us to solve the system, but rather asking us to verify whether or not the given ordered pair is a solution to the system. So a combination of x and y will be a solution to the system if it satisfies both equations in the system. So if we want to check, like with number 1, whether or not 3, 4 is a solution, we're going to substitute in 3 into x and 4 into y into both equations, and it has to make both equations true. Even if it just makes one of the equations true, it is not a solution to the overall system. So we'll just plug in 3 into x for that first equation. So this equation, x plus y equals 7. We're going to substitute 3 in for x, so 3 plus, and now we'll substitute 4 into y, and sure enough, 3 plus 4 is 7. So what that means is 3, 4 is a solution to that one equation, but possibly not the whole system. Maybe it is, maybe it isn't, but it also has to satisfy the second equation. Another thing that this means is that 3, 4, like if we were to graph the line x plus y equals 7, 3, 4 would be on that line, but we want to make sure it's on both lines, so we do need to test the second equation. 3 minus 2 times 4 is negative 5. The first one was pretty obvious, 3 plus 4 equals 7, but I'm going to actually use a calculator here to verify the second one. 3 minus 2 times 4 is negative 5, so that one actually checks out too. So what that means is that 3, 4 is a solution to the system. Number 2, we're going to be testing negative 5, 2. So just like with the first one, we're going to substitute in negative 5 into x and 2 into y. The first number is always x and the second one's always y. So that first equation, 2 equals negative 5, which is actually just positive 5, minus 3. And sure enough, 5 minus 3 is 2. So it satisfies the first equation. Now let's test the second one. 2 equals 3 times negative 5 plus 10. Well, 3 times negative 5 is negative 15, and negative 15 plus 10 is negative 5. So 3 times negative 5 plus 10 is negative 5, and that is not 2. So this is not going to be, the point is not on that line. And so even though it satisfies the first one, it does not satisfy the second one. So negative 5, 2 is not a solution to the system. It's got to be true for both. Now, when you look at a system of equations on a graph where you essentially graph both lines, you are going to find the solution where the lines intersect. So there's not really any work to show for any of these problems. This one's number 5 is a little vague there, but it's going to be somewhere around there. Basically, what we're trying to identify here is that the solution is that point where the two lines cross. Now, if you're looking at a table of values, it's not going to be like quite as obvious as looking at the graphs, but basically what you're looking for is an XY coordinate pair that is on both tables. So you just kind of have to look back and forth, and if I look at where x is negative 9, y is 9 here, but it's negative 11 on the second one, so that's not going to be a solution. Negative 6, 8, negative 6, negative 2, those are not the same. Basically, you're just looking for the one that is the same, and that's going to be right here, negative 3, 7. So that's your solution, negative 3, 7. All right, these questions are kind of along the same lines as the ones that we did up here, where we're trying to identify the solution to the systems. Up here, we were just trying to identify where they would be, but now we're actually going to cite the point. So we're going to write down the coordinate, the XY coordinate pair that is the solution to the system. So just like before, we're trying to find that point of intersection although these graphs are a little bit easier to read. They've got some numbers on them. They don't look as blurry. It's going to be a little bit more obvious where these solutions are. And they give us the equations, although they didn't really need to. It is kind of nice to see the connection there between the equations, the graphs, and the solution. But really, all I really needed to give you was the graph. And as long as you can identify that point, then you're going to have your solution. So for number 8, you can see that solution is at the point 3, 0. And you can test those into the equations. I'm not going to do that for each one because we did that for the first few equations, but just to kind of give you a little taste, if I tested 3, 0 to that first equation, I'd have 3 plus 0, that equals 3, that checks out. Should check out for the next equation too, but I'm not going to go through all that. Number 9, this point looks like it's at 2, negative 4. Number 10 is at 0, negative 2. And number 11 is at negative 3, negative 1. Now we're getting into the real meat and potatoes of this lesson, which is how do we find the solution if we don't have a graph or a table, and all we have are the equations. So if we're trying to solve a system here, we're going to use a method called substitution. There are some other methods out there. Like if you had taken Algebra 1, you've probably learned about not only substitution, but also the elimination and graphing methods, which I guess we kind of touched on graphing here, but we're not really going to use elimination. And on the TSI2, A2 test, you most likely are not going to run into a scenario where you can't solve it by substitution. There's really not going to be that many systems of equations on the test, but you most likely run into one or maybe two of them where you got to set up 2 equations and then solve it like we're about to. So basically what we want to do here is we're going to use the substitution method, which means we are going to substitute one equation into the other. And so you're going to look for one of the equations that has a variable isolated, and you're going to substitute whatever it equals into the other equation and solve basically one at a time. So like here we've got y equals 10 minus 2x. So I'm going to substitute that into the y in this next equation. I could have went the other way and substituted y minus 4 into x into the first equation, but I don't know, it was just the first thing I saw was the 10 minus 2x. I'm just going to roll with it. So here I'm going to rewrite this second equation, except instead of writing y, I'm going to write 10 minus 2x. So x equals, and then the thing that I'm substituting in here is 10 minus 2x, and then I still have this minus 4. And from here, we just need to solve the equation. So I'm going to start by combining my like terms, and I do have 2 like terms here. I've got 10 minus 4, which is 6. So now I have x equals 6 minus 2x. Next, I'm going to add 2x to both sides to get 3x equals 6. Then I will divide both sides by 3 to get x equals 2. And don't be too quick to just box that as your answer. X is 2, that's certainly correct, but that's really only half the answer. When you're trying to solve a system of equations, you should end up with both an x and a y. So here I've got my x, but I still need to calculate y. So I'm going to take that value, x equals 2, which I just found, and substitute it back into that first original equation. So y equals 10 minus 2 times x, which is 2. 10 minus 2 times 2 is 4. 10 minus 4 is 6. So now I have my x, I have my y. Now I can write my solution as a coordinate pair 2, 6. And that'll be the point at which those 2 lines intersect. That is going to be the only combination of x and y that will satisfy both equations. And since the TSI is untimed, it might be worth taking the extra minute or 2 to plug those 2 numbers into x and y into the equations to test and make sure it's right. But I'm not going to do that right now. Number 13, it looks like both equations have x isolated, so we really can't go wrong either way. I'll just take the first one here, this 4y plus 1 and substitute it into x for the next equation because that's what x is. So here I've got 4y plus 1 equals 5y. All right, here I'm going to subtract. It might be easier. And my first instinct is just to subtract 5y on both sides to get the y over to the left-hand side. But that's going to give me more steps. It's not wrong to do it that way necessarily. But I think it might actually be easier if I bring the y's over to the right. Because then I've got 1 equals 1y. I go directly to the answer rather than, and maybe I'll just write this out temporarily. But like if I were to subtract 5y to both sides, what I'd get is negative y plus 1 equals 0. And then I'd have to subtract 1 on both sides to get negative y equals negative 1. And then divide both sides by negative 1 to get y equals 1. I get y equals 1 both ways. But you can see that it's definitely more efficient to do it this way, that first way. So I really don't want to do it this other way. It works. It's just, efficiency is kind of important, I suppose. Okay, so I've got my y, and now I need to find x. So I'm going to take that value of 1, and I'm going to substitute into one of the equations in the original system. Now, the way this system is set up, they both have x isolated, so it really doesn't matter which one you plug it into. I'm just going to go with the first one. So I've got 4 times y, which I just found to be 1, plus 1 equals x. 4 times 1 is 4, plus 1 is 5. So x equals 5. Now that I've got x and I've got y, I can write my solution 5, 1. Even though we found y first and x second, you're still always going to write the x number first. It's just the convention that we're going to use and that the TSI uses, and really most mathematicians are going to put the x before the y, if no other reason because they come in alphabetical order. Okay, we've got just a few more examples here for you. Number 14 has y equals 11 plus 4x and 3x plus 2y equals 0. Notice how on the first equation, we've got the y isolated. So that's the one that we're going to start with. We're going to take that 11 plus 4x and substitute it into y for the second equation. So we've got 3x plus 2 times, and instead of y, I'm going to write 11 plus 4x equals 0. So notice I'm taking that 11 plus 4x, sticking it right there, and writing 11 plus 4x instead of y. That allows me to just have one equation with a single variable. I don't have a y, so now I can solve it like I normally would. So I'm going to first distribute the 2, giving me 3x plus 22 plus 8x equals 0. Now I'm going to combine like terms. I've got 2 like terms here, the 3x and the plus 8x. That's 11x. Next, I can subtract 22 from both sides, giving me 11x equals negative 22. And finally, divide both sides by 11. So x is negative 2. Now, once you have the x, or you don't necessarily need x first, but as soon as you have one of the variables, you can take that number, in this case, x equals negative 2, and substitute it back into the equation that has the y isolated. You can technically plug it into the other one as well, but since y is isolated on that first equation, it just is going to be a lot easier to find than if we try to find y with the other equation. Won't be too bad with the other equation, but it's definitely easier this way. So y is 11 plus 4 times x, which is negative 2. So y is, and again, I'm going to use the calculator here. Don't be shy about using the calculator. 11 plus 4 times negative 2 is 3. So now we have x, we've got y, so we can write our solution, which is negative 2, 3. Number 15 is set up pretty much the same way 14 is. So we're going to take the same basic structure as far as what steps we should take and do kind of the same thing here. So really we're just practicing the skill of taking one equation, or at least a piece of the equation, and substituting it into the other equation. So I'm going to plug this into y and rewrite this as 4x minus 2 times 2x minus 5 equals 10. Then we're going to take pretty much exactly the same steps as we did before. Just be careful on this distributive property here. We are going to distribute negative 2. That minus kind of goes along with it. So just that's something that I notice students make a mistake pretty often on, is they'll forget about the minus on there and just distribute the 2. Usually they'll get that 4x, but I see pretty often they kind of miss the negative on the second multiplication here. So we do have negative 2 times negative 5. That's going to be positive 10. Next, I'm going to combine my like terms. 4x minus 4x. Now that is just 0. So those go away, leaving me with just 10 equals 10. Now, if all the variables drop out, we've seen this happen before on just single linear equations. And in the lesson, we touched on it a little bit, but just remember that if all the variables cancel out, you're either going to be left with a true statement or a false statement. If it's false, like the example we did in class, there'll be no solution. But if it's true, that means the two lines are coincident, and therefore there are infinitely many solutions. This is always true. This is what we call an identity. Okay, so we say there are infinitely many solutions. Now I want to caution you here. When we use the phrase infinitely many solutions on a single equation, what we really meant to say is that any number could be a solution. Now with this system, there are infinitely many solutions in the sense that there are infinitely many different combinations of x and y that will work for both of these, because ultimately they're just the same line. So any point that's on one line would be on the other. But that doesn't mean every combination of x and y will work. In fact, if you're just sort of like randomly picking x and y, odds are it's not going to work for either one. But any point that's on one equation will be on the other. There will be infinitely many of those. So there are infinitely many solutions, but it's not okay to say that every point on the grid is a solution, just the points that are on both lines. Number 16. We've got a y isolated in the first equation, so we'll definitely start with that. Negative 5x plus 3 will be substituted into y for the second equation. So 15x plus 3 times negative 5x plus 3 equals negative 3. We'll use the distributive property. And it looks like we're going to get another special case here, because we got that 15x minus 15x. 3 times 3 is 9 equals negative 3. We'll combine our like terms, but this is going to go to 0, leaving us with just 9 equals negative 3, which obviously is false. Okay, these two numbers are not the same. We call this a contradiction. I don't know if I can spell that. There we go. And so, on the previous problem, we had all the variables drop out as well, but we got a true solution, a true statement, right? 10 does equal 10, but 9 does not equal negative 3. So if all the variables cancel out and you get a true statement, you'll have infinitely many solutions. But like in this case, if the statement is false, then you're going to say there is no solution, meaning there is no coordinate x comma y that works for both equations. Geometrically or graphically, the way that you can interpret that is that you must have two lines that are parallel. In other words, they never intersect. So there's never going to be a point that's on both lines. Number 17. Now, this one is going to be a little trickier than any of the ones we've done so far. It's not too bad, But notice how on neither equation is one of the variables isolated. So you're going to have to do a little bit of work up front to force one of the variables to be isolated. And there's not really a rule as far as like which one you have to isolate. Like for example, in the first equation, we can isolate y if we divide both sides by 5, right, to get y equals 2. Or we could solve for x in the second equation to get and add 3y to both sides to get x equals 4 plus 3y. Either one's fine. And on this particular problem, it looks like solving for y is going to be the way to go, just because the equation is much simpler and you actually get the y value right away. But in general, there's not like going to be like a hard and fast rule of which one you have to go for. You try to isolate whichever one's the easiest, as far as, and that's an opinion question for most of the time. But I'm going to go with the first equation, and really the reason I'm going to pick this first equation is because I actually don't have an x in there to begin with. So if I divide both sides by 5, I'm going to get my y value without actually doing any substitution at all. I get y equals 2. Now we still need to go back and substitute this into the other equation like we normally would to find x, but look how easy that was. Now this won't happen very often where you have a system and like one of the variables just isn't in one of the equations, but it will happen occasionally. So I'm going to plug this into the second equation because the first equation really won't do anything for us since there's no x. And so I've got x minus 3 times y, but since y is 2, I'm going to replace y with 2. And now I'm going to solve for x. Negative 3 times 2 is negative 6. And then if I add 6 to both sides, I get x equals 10. So now I have my x, I have my y, I've got everything I need to write my final answer. The solution to the system is 10, 2. And I think, oh, nope, that's not it. We're not done yet. Okay, got a little ahead of myself. I thought that was the last one. But we're going to do a little TSI prep here. So I think this is the last one where we're just solving a system and you got to show all the work. It's not multiple choice or anything. And you come up with your solution. If you have any questions about the steps here, please reach out to me and I'll try to help you out. But before I let you go, we do have a few more problems here. We do a little bit of TSI A2 prep. These are going to be problems more like what you could expect to see on the TSI. So let's go through these. 18 says, what are the coordinates of the point of intersection of these two lines? And so it is multiple choice. And so I do want to solve this out like the normal way, but I also want to, once we're done with that, kind of show you how you can answer this even if you forget how to solve it algebraically. So my system has two equations, y equals x plus 4 and y equals 3x minus 4. And so just like when we had a system up above, we're going to take one of them, like I'll take this one, y equals x plus 4, and substitute that x plus 4 into the other equation. So that's y. So I'm going to substitute that in for y in the second one. Effectively, basically what we're doing here is we're going to set the two equations equal to each other and solve for x. So I'm going to subtract 3x from both sides to get all my x's on one side. That'll be negative 2x plus 4 equals negative 4. Then I can subtract 4 from both sides to give me negative 2x equals negative 8. And then divide both sides by negative 2. That's going to give me my x value, which is 4. Now, you're not going to be in a rush on this test. I've said many times before, this is an untimed test. But look at our answer choices. Only one of them actually has an x. So we should be pretty sure at this point that the answer is going to be C. But I do want to go back and check, especially on these where, we may have made a mistake somewhere. We want to make sure that the y ends up being 8. So I take that x equals 4, and I plug that into, I could plug it into either equation, but actually that first equation looks a little simpler. There's less stuff going on there. And y is going to equal 4 plus 4, which sure enough is 8. So that checks out. Our answer is C. Now let's say you're in the middle of the test, you kind of have a brain fart, you just kind of forget how to solve this algebraically. Maybe you do remember what it means to be a point of intersection, but you just forget like all the algebraic steps because there are quite a few here. You can still get this problem right using a different strategy. Because it's multiple choice, you can always use those multiple choice items, take advantage of the fact that it's multiple choice, and use them by plugging them into both equations like we did at the very beginning. Okay, the very first couple of problems were just asking us to test an answer choice to see if it worked. That is the strategy I think you should probably go with if you're feeling at all uneasy about your algebra. So in other words, like let's test A, for instance. I'm not going to go through all of them, but if we're going to test A, x is 2, y is 4. So I try the first equation. So 4 equals 2 plus 4. And that doesn't work. So I know that it's not going to be A. I could test it with B. Okay, I'm letting y be 6. So 6 equals x, which is 3 plus 4. That doesn't work, and so on. And so you're going to see that the 4 and 8 definitely works. The 5 and 10 does not. So you can get away with just basically going through the answer choices, seeing which one works, and that way you can skip the algebra. Alrighty. Number 19, it says, which of the following graphs best represents a system of equations that have no solution? So we discussed earlier that a system that has no solution is one where the lines will never cross. And we see 3 out of the 4 graphs here. There's no intersection point visible, but you could imagine like C is probably the most obvious one, that if I keep these lines going, they're going to eventually cross. So it's not so much that you see the intersection, but that there could be an intersection at all. So the only way for there to be no intersection is if the lines are truly parallel. So right here, we can obviously see B is not going to be the answer because we can see the intersection point right here. C is not going to be the answer because we can clearly see they will eventually intersect. So we're looking at A and D. And you might be able to see that A is not going to be the answer. But if you're not sure if they both just kind of at a glance look parallel to you, you can check the slopes. In order for 2 lines to be parallel, their slopes have to be the same. So like if I check D, which is going to be our answer, by the way, the slope of the top line looks like I'm going down 2 over 5. So the slope is negative 2 over 5. The slope of the bottom line, if I try to find a point here, I guess this one will work, go down 2 over 5. So they're both 2 over 5. However, if I check the slopes on A, it looks like the top one's going down 2 over 4. So that'd be negative 1/2 or negative 2 over 4. But if I check the next one, it looks like it's going down 2 over 3. So the slopes are not the same. And it's not as obvious as answer choice C. But if you're not sure, you can always check the slopes like that. All right, number 20. How many years after planting will the trees be the same height? Well, they're only the same height when their heights are equal. And so this one is just really more of a matter of just like reading the graphs and understanding that they're going to be the same height when those 2 lines intersect. And so the answer here is 4 years. All right, I think that about does it for tonight's homework. As always, please reach out if you have any questions. Come see me in the morning for tutoring. Shoot me an email, comment on this video, somehow reach out to me, and I will be sure to help you out. But otherwise, y'all have a great day, and I'll see you next time.